Hello, my friends, and welcome to the stream. Um, Today will be a somewhat relaxed stream, uh, and it will probably be broken down into several parts, since I am in fact a bit wasted or tired or whatever we call it. So yeah. Um, Anyway, let me just get sorted in terms of a bit of music here. Um, so, during the last episode, we implemented the movement system that uh, is able to calculate different bounds for one in terms of the highlights, and then secondly, in terms of the available move sets. Okay, so um, and we would like some kind of attack system. So whenever we select select a unit and we calculate the whole what do you call it, movable tile set. I just realized that we would probably want to be actionable, call it actionable tile, since we will be using maybe we just want to call it tile, and okay. Let's just rename some types here. Maybe just position. Board position. Maybe we want to do that instead. Yeah, it doesn't really matter much, but it will just make more sense if we do it this way. And let's create a vector of some tiles, board position, calculate attackable tiles, and we put in a game state, and a const unsigned in for the unit index. Basically, we want the same logic as this. But we want to change this. Okay. Let's see. Okay, let's do a vector here. Attacks. And pass in. Hello. Let me see my. Let me just fix this chat here. Okay, now I can see the messages, but I don't know what that actually meant. Okay, but so we calculate the attack X and the attack Y. And let's do attack 1. And let's do so a pawn will be able to attack like this. And let's pass in the coordinates here and check if they're in bounds. Okay, and we add the attack. Secondly, we create a set where, which is the, let's see. Okay, so it's definitely +1, but on the Y, but then it's -1 on the X. Okay, so this will check whether, what do you call it? There are any attackable, um, um, what do you call it? Uh, board tiles. Right now it won't check for any units. That is completely fine. We will add that later. Let's see. I'm unsure whether I actually use this. Calculate attackable tiles. There we go. Create move highlights. And we could add a yeah, so this only changes yeah. Maybe we want a different function here. That still returns a vector of materials, create action highlights in the game state. Yeah, let's just do a method that simply takes our movable tiles and our uh, attackable tiles and simply spits out this, but does the same thing for yeah, I should really do the enum anyway. Anyway, uh, we'll create some action highlights instead. Okay. So we calculate the attackable tiles, we calculate the movable tiles, and we collect our entire highlight. Create actionable with our game state and our moves and our attacks, referenced of course. And let's see what happens. And as you can see, we do get attackable tiles highlighted. Okay, let's try it out for this one. Yeah. So We calculate our attackable tiles. And let's do a let's just do a small method that wraps the whole thing. Has opposing unit constant sign int x and constant sign int y maybe. Bool found false, and we will return found, and we will simply grab our game state here. Let's see, units. We also want a constant sign int. Nah, we can access it from the game state. If game state units I player unlike equals game state active player, we will continue. Or the unit X is unlike this, the otherwise we will set found equals false, true, and we will break. So if it's not the active player and the X and Y is the same, we found the unit and we break out of the loop. And of course, we don't need to check the X and Y if it's not the opposing player. Okay. Let's see. Has opposing unit. Game state. Attack x1. Or rather, attack 1x. Okay. So this should simply, well, that doesn't work for some reason. Let's try stepping through it. Okay, that skips the line. Okay. Let's see. I mean, the first unit. And our X and Y 3 and 6. Well, for one, the player shouldn't be the same. Let's see, game state, units. Huh. Now that is, whoops, a bit weird. And the X and Y. Huh? Let's just check for this initially. Yeah. This won't be true. Which is fine. The X is 3. Okay. Let's try swapping the Y. Did I just mistype it before? Maybe. Yeah, I probably just mistyped it. Let's see. Oh yeah, I didn't check the Y actually. That's why. Okay, I just mistyped it. Okay, so we have no attacks, but now, yeah, the dash part is not checking for the possible attack, but this algorithm, or rather this check here works now. And we of course need to add it to this one. And now our attack highlight should be ready. Yeah, as you can see, I can move here and I can tag this unit. Great stuff. Yeah, and if we swap to the other player here, you can see we are able to attack this pawn here, and we're able to move. And as soon as we move past it, we can't attack it anymore. Okay. 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 Let's see. Next, what do we want to do? We should do something like maybe an actual attack. Yeah. Right now, we're able to actually, I just wanted to disable this since we're not really using it right now. Okay. It's more related to rendering and editing of objects. Okay. So when we select our unit, we can check if there's something available to attack on that board position, and we can highlight it as a red square. Right now it doesn't do anything. And attacking is something that we would want to handle in a different stage. So we didn't click on a board tile. We clicked a unit. And it's not the same unit as before. We clicked a new unit and it's ours. And we want to check if we clicked a unit that isn't ours. And this is probably one of the last states we want to handle. So we want to check if the thing is within this particular unit's valid attacks. Let's see, is has opposing unit, and we pass in our game state reference, right? And yeah, for one, if we click the actual unit, it should count as a valid attack. Otherwise, we will click a board piece, and the logic should be up here. So we will simply pass in the X and Y. Yeah. And let's just print it out. Attacked unit. So let's try that. Yeah, we attacked the unit. Okay. And of course, we could do some logic here. And let's call this movable. Also, we need a restriction on our moves. And we actually want this to be handled. And we check whether it has a unit. Of course, we can't move to it if it has a unit. So whenever we get into this state here, we will already have checked whether the tile is movable. And we can do a check on attacks. Hello, buddy. How you doing? Let's see, print attacked unit by tile. Click. Let's just do something like that. I'm pretty good as well. Bit tired, but it is what it is. Okay, so okay, now I click the unit, of course. Okay, so if I click the board piece here, yeah, you can see we actually do the attack. And we want some kind of method. Yeah, how's it been? Okay, so whenever we attack, we want to update the game state. So let's do something like a void attack, make attack, and pass in our game state pointer. And maybe a unit index. Maybe. Oh, how nice of you. And that sounds great. It's always good to do a bit of learning before you go to sleep. Get that information stored in memory. Yeah, sure thing, buddy. Thanks for dropping by. Okay, so this will be the actual opposing unit. Or rather, let me just yeah, this one tracks the actual unit index. Um, so right here, we did click upon if our previous selection this of course let's see, so we clicked a new unit. If if the game state units, game state previous selected index. First of all, let's see the index. Okay, so this needs to be valid. Uh, is the active player. So if we previously had a pawn selected and the active that controller, player controller, rather pawn controller is the active player, we're currently in a state where we could actually do an attack right now. This will mess up if we're like doing something. Oh, wait a minute. No, it's not. We're getting a crash instead. um, there we go. Okay, we're still getting a crash somewhere. Let's see. Maybe it's this part of the code here. Let's just check if it's our check. Yeah, it's our check. Because if I disable this, it won't care. Yeah. Oh yeah, this of course needs to be subtracted by the number of board tiles. That's why we're having a memory problem. Okay, as you can see here, I'm actually allowed to attack this even though it's not in range. So okay, so if we're actually if we're in a state where I'm unsure whether it should be part of this generalized. No, because we want to be able to click opposing pawns without attacking them to, for instance, get displayed some information about that particular unit's stats or whatever, if we decide to implement stats or special abilities for the chess pieces. So being able to click an opposing pawn is fine, but if we are in a state where we previously had selected one of our own pawns, which is this check here. Um, and let's just actually calculate the. Okay. Let's do a unsigned int unit index, which will be our previously selected index minus the number of board tiles. And we will simply use it right here. Okay, we calculate a series of possible attacks for this particular unit. And then we can simply ask let's see, let's call this previous unit index, and then let's iterate over all of these potential results. And simply check if the clicked unit index here let's see, game state, unit, let's see, bool found equals false if the x is equal to the attacks I.x and the game state unit index here dot y is equal to the attacks I dot y. We found the attack and we break out of the thingy, and we can now instead do if found. We do like that. Check, simply call the attack. So if we run this and we click here, select our pawn, we can no longer create an attack by clicking the pawn which is out of range, but if we move into range here, we can click that and attack it. Also, our previous method by simply clicking the board. You did DSA, what does that mean? But yeah, our attacks actually work now. Also, we can test it by using the opposing pawn here by swapping the players. Okay, and everything seems to be working. Okay. And in our game state here, when we click next turn, we actually want to set our previously selected index and our uh, selected index to -1. So just what do you mean exactly by that question? Yeah, I built everything here in C++, if that's what you mean. Okay, so if I select that pawn, uh, it of course needs to, what do you call it? Uh, Reset the board state. Let's see. Okay, if I swap the turn, it resets, but it doesn't reset this one. So let's update the debugging information as well. So it should be like if I press next turn, oh, it still doesn't update. Haha. Okay. And let's see. Let's just maybe. And let's do something like a reset method here if. Oh, maybe we just want to actually. Let's see. Set the selected index to -1 and then reset this afterwards. Maybe that will clear the cached information. No, it still doesn't. Yeah, so I could also do if index, let's just do a return here. No, maybe not. Yeah, maybe there. Wait a minute. Yeah, so when this changes, we want to set the let's do an update where we set the let's see. Yeah, now it deselects. Great stuff. Yeah, it doesn't need to remember what was previously selected since we swapped the turns. Yeah, so nothing is selected. And maybe we don't care about resetting the previously selected value because it will get flushed whenever we select something. Yeah. I've been doing programming for as a hobby for maybe 1 or 2 years, but yeah, just as a hobby. So okay, so last thing is we'd like to actually what do you call it? Um, Handle our actual attack, and this data packet here just gets sent into yeah, the problem is that we send our drawable packet here. Maybe we want some logic in this. Maybe we want a buffer of sorts that of sorts. I think it's pronounced like that. That keeps a set of active meshes. Hmm. Yeah, that is the problem we encounter when our system was built from the renderer and into an application, but actually now we want to handle the coupling the other way around. Now our game is the actual kernel slash core of the program, which needs to dictate whatever we should draw to the screen. Um, so we need to change the way we handle rendering. After the game loop here, everything should be more like right now we simply draw whatever resources we have created, but we don't want to do that going forward. Instead, we would like to um, actually submit the whole thing, because yeah, maybe we even want to change this workflow here. Yeah, yeah, maybe we want to change that workflow entirely. So this function here is probably still fine, but we want some way of controlling the drawable meshes here. Right now we kind of like create the drawable meshes and well, let's see. Yeah, we actually create the matrices themselves during runtime for each frame. Yeah, this is fine, but the way that we can manipulate the buffer probably should change. Create drawable mesh. Let's see. The problem is that yeah, this workflow is problematic. Um, this is also a problem that we will encounter in terms of calling. Okay. So how to solve this? Yeah, it would also decouple this whole thingy. Let's see, so maybe we want to do some kind of double buffering system. Yeah, I'm unsure whether I should do it one way or the other. We could do something like, if it's not active, we skip it. So bool active, true. If it's not active, drawable, we simply continue. So if we, for instance, invalidate Let's see, a const unsigned int index. Let's try doing something like that. Instance drawable meshes. And let's try let's try invalidating the mesh here. Okay, but it definitely deleted something. And we have a pretty large performance drop. So it's probably related to branch prediction of some sort of, yeah. Yeah. Ah. For some reason it deletes the tile instead. Ah, wait a minute. Yeah, it should just take index here. There we go. But it's somewhat slow, right? Yeah. Yeah, I'm not sure I like this method. Yeah, I'm not sure I like it. Okay, so let's change that. Let's do a different method. Where we um, change this stuff here. So let's do void submit drawables. Yeah, maybe we want to do that instead. Ah, yeah. I'm not sure how to most elegantly solve this. Um, the problem is that we have two systems now, and does it post any messages in terms of errors? Because no, we don't get any errors in terms of output here, but we do get a pretty large. Yeah, and the ABB still is present. Yeah. Yeah, so we need to refactor some of this stuff here. Maybe, so we need some kind of frame cache, right? Yeah. Yeah. All right, I'm gonna think about this problem maybe over some food. So, yeah, I mean, I'm just contemplating what would be the faster way to do it. And maybe I need a break to decide on that. But when we do when we upload our draw data, we simply copy the camera view projection matrix, and then we copy each transform and register a series of draw calls into a frame buffer for the renderer backend. And we use these draw packets here. Which is basically indexes into our vertex and index buffers. And the renderer frontend itself knows which material which gets sent to the shader alongside with the actual transform. Okay. So our renderer front end right now we simply but I mean the transforms themselves doesn't really do anything, do they? I mean this whole data slot here inside the renderer is mostly I mean, the problem is right now that this check here, I'm pretty sure, is messing up the whole thingy. Yeah. Maybe we do want a double buffer of sorts. Maybe we don't want to. Also because we're doing actual computations. This is a series of CPU instructions that compile our matrices, and then we multiply them. And that is fairly math heavy, and the CPU right now can interleave these copy instructions with our actual computations, which are vectorized. So if we do an branch prediction right here, this is a major slowdown. So maybe we want to actually handle the reshaping of this vector here outside of this for loop. Yeah, well, obviously we do, but I'm just considering how to compile the information most efficiently. I mean, this won't be as slow if we don't have branch prediction here, and yeah, we grab the actual mesh data here and create a draw packet. Huh. But we do calculate the transform, which is most of the heavy lifting. Yeah, maybe I just need to rethink this a bit. Okay, let's just try something out. Yeah, we can always not do it. Okay, so let's see. Our application will have a series of, right now, tiles. Yeah, I think I'll refactor this. Yeah, instead of draw index. Right now we will leave it left for now. If we change to the dynamic submission, this should be color named otherwise than material. For dynamic submissions, should be changed and maybe contain a material slash color slash texture. Okay. Okay. Okay, inside our application, when we initialize, no, when we create game, we create the materials. Oh, whoops. When we create the mesh, yeah. Okay, so let's use that. Okay. Okay. Draw data. Okay. Does it know about a frame state here? Probably not, right? Yeah. Yeah, we probably don't need this anymore, but doesn't matter. Um, Controls. Um, let's see. Buffers slash caching. Maybe we want uh, do we want something like that? Okay. Let's see. So when we click here, we do a recast. Yeah. maybe the maybe the yeah, maybe I should change all of it. Maybe the bounding volume itself is not something I should store in the renderer. Yeah, maybe the renderer itself actually only wants materials and meshes, eventually textures, effects, and so forth. And maybe this is not something that we want actually as part of our renderer. Okay, so when we create the game, we load the meshes, the materials. This is fine. This is also fine. We create the boards itself, but this part here should probably not be added. I think we'll have a crash right now, but no, okay, not yet. But if I click anything, of course we will. Okay. Let's do something like um, what we have on the renderer side. Drawable mesh. Uh, okay. Float x, y. So this is some kind of packet. Does this actually have the renderer? Yeah, it does have the renderer. It also owns a instance of the renderer, right? No, it actually doesn't. Yeah, it doesn't need to know about it, so I'm pretty sure this could be moved into Let's see. Okay, let's see if everything still works. Still works. Okay, so instead, let's create a type inside the renderer here. Resource types, trouble mesh, ABB, blah blah blah. Struct, front end. Renderable mesh. Let's see. Let's see. Okay. Let's see. Okay. So if we maybe the application actually wants some sort of knowledge of um, yeah, so the resource types here. Let's see, renderer. What did I call them? Renderable mesh. Oh, I need to prefix it. Right? Call. Okay. Mesh buffer. Okay. Let's do a for loop. First, we need to do the game state dot mesh buffer clear here, and then we do an unsigned. Yeah, we do iterate. And then we do unsigned int I less than game state that units I plus plus. And we could do something like a tile yeah. Let's see. Temp mesh. Mesh equals uint 32t here. Let's see. Origin. Well, I'm not sure. Position, let's call it that for now. Let's copy this call here since it contains a lot of the information. The position X, Y, and Z are the first three components. Times 2, and then the Y 0, and then this gets repeated. Let's see, not the last one, but okay. Okay, so we calculate the position of the tile itself, and we add them to our frame buffer. Push back, temp mesh. Okay, for now this should it won't work, but we will add a method on the renderer side that or rather we will implement the rendering side submit drawables game state mesh buffer by reference. Okay, so when we submit this yeah, we basically want to actually swap these. Okay. Whoops. Okay. We basically copy this. Copy this. Dereferenced. And does this actually work? Just straight out the box. Well, no, we we don't get. We do get the draw call itself. Everything seems faster. I don't know if it's what it's related to. Anyway, uh, probably just less. And let's see. We don't want this anymore, right? Since we're computing the transforms anyway, we maybe we want scale as well. Scale.x. C C of course. Y. Okay. Does this actually work? It does work. Yeah, right now our picking algorithm is entirely messed up. And it doesn't seem like we had any slowdowns actually. Which is pretty great. So We might even have a small increase in speed. Okay. So now our application simply submits each drawable. We would like to do something of the sorts with the units themselves. Let's see. Let's not add the position right now. And R, no, R. Let's do something else here. We will disable this. We will. Hello, buddy. No, I haven't. What is the concept? Let's just do material, yeah. And the unit gets set up with an X and a Y. Okay. And how do we actually calculate that? Yeah. We need to remove that. Stop doing that. Can't remember. So 0 and 1 are the black and white. Uh, let's just do like this. Yeah, so let's see. Okay. And the C is right now hard-coded for these kind of pawns here. We should definitely change that in the future. Oh yeah. Let's add the float cast here. Just to be explicit. Okay. Well, we need, of course, to set the mesh index. And, of course, change this index as well. Okay, the scaling is messed up. And the scaling is available here. Okay. Scale. Okay, and yeah, this is the problem. Okay. In terms of rendering, we're back in the previous state here, where all of our meshes get actually drawn. Right now we have dynamic submissions instead of the renderer actually holding this information here. We simply, yeah. Okay, so we need to refactor that as well. But yeah, we went from the renderer being decoupled from the actual game information into a system where actually our game state here controls everything. Also, the information gets parsed for every frame and sent to the Oh, I should check it out then. It sounds interesting. Also, this will allow us to modify our code. I should probably um, I should probably hmm, I should probably update some of the bounding volume stuff as well. Technically, a bounding volume is not something that should reside inside the renderer itself. So yeah, it probably makes sense to migrate it into the application itself. Okay. So the application will store the AABBs, and when we're done with that, we can actually work on re-implementing the debugging information. Yeah. Let's see. Let's scope this. Application tick draw call. Submit draw calls. Okay. So now this scope here does all of our draw call submissions for the game. Next, I'll have to refactor the AABB system. Okay, so whenever we create a unit here, we actually want some part of the logic that was residing inside the renderer. Actually, this should go out of, or rather, get removed. It also makes our renderer front end a bit more clean without all of the clutter. Okay, so whenever we create a mesh, this is fine. This should still be here because I want the actual mesh information to be part of the renderer front end. So the renderer front end should contain meshes, materials, textures, probably lights, um, maybe some post FX stuff. Yeah, definitely lights, but and the AABB stuff is basically more something that is handled in the application, the game itself, and also used in um, different systems. So it's better if the application actually handles that information. Yeah, the renderer should simply just draw stuff, handle effects, and draw stuff. It doesn't make sense that it handles collision stuff, but the AABBs are very handy in terms of calling, frustum calling, for instance, on the application level. So if we wanted to check if something was not visible to the camera, we could do frustum calling before even submitting the draw calls and not taxing the GPU or the CPU by registering the draw calls themselves. So that's also an argument for handling all of the ABBs outside of the renderer itself. Yeah. Anyway, I'm blabbering about. Um, okay, so I simply store the. Oh, thank you. Uh, so I'm trying to figure out what I want to do here. So the meshes themselves actually contain a series of information about the sort of original or um, pre-calculated bounding volume, and it gets generated whenever I create the actual mesh. So we calculate the AABB from the most extreme points of the mesh itself, and we store that on the actual mesh. So the mesh AABBs are like the original bounding volume for that particular mesh that is tightly fit around the mesh itself, all of the vertices and so forth. no, so we have that information available whenever we create our objects. So we could do something like um, we could also just do something like static inline vector mesh reference get meshes, and where we return our instant meshes, because then when our application here calculates our game objects, it can actually fetch the AABB and alter the what do you call it, information, and store it. So we load the mesh into the renderer, we get the index, and these should be mirrored, right? No, wait a minute. Yeah, we actually have the mesh lookup ID uh, since it's right here. So let's do something like core bounding ABB, ABB, and get meshes here could be used, and we could downcast this UUID into the actual index, and we would have the ABB information right here. So we basically need to copy. Let's see, we could do something like what is the type called? The type is called yeah, I'm not sure we actually want. Yeah, there's no difference now between these two. So yeah, let's just remove that. And wait a second in terms of implementing that, and you should show me some error codes. Oh well. Is it not stored on the temp mesh? Yes, it is temp mesh. Yeah, but it doesn't care about the type, of course. Okay, so we have no problems yet. Okay, so let's just grab a pointer. P mesh ABB and give it our address of our ABB. And we simply pmesh ABB, copy the half widths and the origin itself should be our information. Oh, I'm not doing it for the actual tile itself. Okay, let's start out by doing it for the yeah, let's start out by doing it for the chessboard first. Okay. Tile UID, let's just do like that. And I actually forgot to add the tiles. Oh no, wait a minute. I'm pretty sure it's just using the default mesh. Oops. Okay. Yeah, we need to store that one as well. Okay, so we will calculate the ABB here. So the thing is that our what do you call it? Half widths will be the same since we're using the same mesh for all of the tiles. But the position will have to be calculated like we do down here. So we set the center. I hope the compiler collapses this. Otherwise, we just do something like unsigned int. Unsigned int index equals 0, and we set the index to this value here. There we go. Gets a bit more readable as well. And we can, since it's already in cache, we can access it pretty quickly, I think. Okay. Okay, so we calculate the ABB, and then we simply game state. Whoops, it's not supposed to be called M. And let's just do lowercase ABBs. Push back and add our AABB. Okay. So we actually create our AABBs here. Next, in our raycasting algorithm, we should simply pass in our game state here, AABBs, and disable this since we won't be needing it and we're not using it anywhere else. Okay, let's see if we can at least click our tiles without crashing. Okay, we have a problem. Maybe this needs to go before the mesh struct, but probably. Hello, how are you doing? Yeah. Okay. Okay, we can't click it yet. Let's see, do we... okay, we don't have any information about it. Okay, let's try stepping through, seeing what happens. And let's see, do I not have a this game state AABBs? We have 64 of those. Okay, what's the problem? Ah, yeah, okay, we use a method here that should be disabled. All of these should be disabled since we're not using them anymore. Actually, we will have to redo that, of course, but okay. So selected tile gets updated up here. Yeah, so now we can click our tiles. We can't click the pawns yet because we haven't implemented the uh, actual calculation of that. Okay. Create pawns. Let's just and let's scope that just for good measure. Okay. Pawn index. Let's rename it to that. Okay. And let's push back the ABBs, but recalculate their centers. Pawn 2. Pawn 1. And let's see how we calculate the position. So the ABB center here, whoops. And let's set this. Okay, so now we should be able to actually click our pawns. Selected unit 0, selected unit 1, and we can select, whoops. Okay, I don't know what. Oh, I forced a move. Of course, that doesn't work. So, yeah, that's the problem. The movement logic also needs to be updated to handle our new renderer coupling, but I'll do that in a bit. Okay. But at least now the mouse picking works again. Okay. So the raycasting works. Okay. Let's see, where do we actually have a oh, update materials here. And let's not use this one. Okay. Let's see. Okay, so the move thing doesn't actually happen. Uh, let's see. Okay, let me just add some debugging here. DXC call print. '65, '64, '62, '60. Oh, for some reason. Oh, yeah, okay. Now I know why. You can't see it because the debug information is not available, but I need to scale the actual pawns here. I'm gonna do it manually. So in theory, or in reality, there's a very, very large AABB here that is blocking the view, which is why nothing works as intended. So it's because we scale down the model, but we also need to scale down the actual bounding volume. So let's see, let's set the half widths and update them. Okay, the DirectX math. Let's see, DirectX math, load 3, multiply. Okay, whatever. Let's just do it like this. There we go. And we're back. Ah. For some reason, well, it doesn't work as intended. Let's see, did I mess something up here? No. Oh, swap here. Oh yeah, okay. Of course, whenever I update the thingy, we need to update the transform, or rather the AABB as well. Okay. Let's do a std vector. No. let's just have it. Let's create a move unit, and we simply pass in a game state, and we pass in the unit index. Okay. And let's do a const unsigned int x, const unsigned int y. Okay, so the game state here. Units, unit index, yeah. That x equals x, and set the y as well. And then we want to calculate the AABB. Okay, I just lost focus. I'm probably in need of a break. But anyway, we will update the position alongside the, or rather, for the AABB. Maybe we want click index here. Let's do unit index, game state. Um, select index. Yeah, okay. Because our select index will actually be our game state, ABBs, and we will recalculate the center here. Let's see. And let's just pass in the X here. And then pass in the Y. Not a dot here. Anyway, okay. So whenever we actually want to move the unit, we pass in the game state by reference. We pass in the selection index. we pass in the x and the y here. And let's comment out this. Okay. Whoops. Okay, we have a problem. Let's try checking that out. Okay, so we step into the select index is 44. The unit index, oh. Yeah, okay. Yeah, okay. Yeah, we want the unit index here. But no. Yeah. Yeah, we want the unit index. And we will simply calculate this from the unit index plus these two. Yeah. And let's do a unit index here. Okay. And we're back to everything working. Okay, so we are able to move our unit here. This is the only place where we do that. Okay. Okay, so we have our moving updated. We have our all of our stuff here updated. So what's left to do is actually re-implementing the highlights. That's fairly simple since we have our original tiles cached. So we simply add a field here, which we call UN32 active material. Maybe we just no, we don't change anything here since we have the original tile set stored. Okay. Let's see. Okay. So we create a method. Reset void reset tile color. Game state. And we simply do a unsigned in I with a game state. Game state tiles dot size. and we set the game state tiles at I material to our game state original tile set cached at I. All right, and that's simply it. And we pass in our game state here. Okay. And next we want to create the actual highlights. And we simply create actionable highlights. And instead of doing this, we simply modify the, let's call this set actionable highlights. Let's see. Let's set our let's set our game state. Oh, wait a minute. Yeah, the index is correct, but game state tiles at index material equals 4, and this is equals 2, and we delete this. Okay, so this will update the material. Let's see if that works. Oh, we need a void here. Okay, that works at least for this part. Okay. Oh, wait a minute. Of course. There we go. Yeah, so we're back in a state where that works. That's pretty easy because we simply update the game state and the renderer just knows or gets the information later on. Okay. Okay, we reset. And we want to reset as well here. We want to reset as well here, and reset as well here. So now when we click something else, yeah. Okay, so the last thing I'd need to do is to re-implement the whole what do you call it? Also at this one. Yeah. So let's see. Let's remove this. Let's remove these functions. Okay, these needs to be disabled. Draw debug. Uh, yeah, I would probably do some version of that where we reuse some of it. Also, a lot of this should be removed. Maybe let's try removing some of that. Yeah, I'm not using that anymore. Let's remove this. Okay. 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 Um, okay, so if we do call the draw debug, um, yeah. So maybe we want something like a buffer for the debugging information that because uh, to calculate the bounding volume vertices for each frame for several meshes, it's just super wasteful. I would rather when we actually move an object, for instance, when this application call here gets called move unit, that it has some kind of like debug mode uh, flag, or maybe a void update. Yeah, I don't know. Maybe some calls to the renderer itself to update the uh, debug information. Let's see. Let's just clean up this. We're not gonna use this anymore, I think. Uh, create objects. Yeah, that's also deprecated, or rather, not even deprecated. It's just removed. Okay, so the draw debug, yeah, it's probably fine. Create mesh. Yeah, that's fine. Okay, draw debug should be something like, let's remove this. And re-implement this. So, draw debug, we want some kind of like, uh, what do I actually use? I use a debug primitive, right? Frame data, debug primitive, debug packets, and the vertices themselves. Yeah. Okay, let's create a function that is called static void create ABB debug info. Um, ABBs. Correct. And let's move this actually down here. Okay. Let's move this down into this scope here. Okay. And dereference it, of course. Okay. Let's do a we will redo this. It will be created as a green bounding volume. There we go. There we go. Okay, so we build our, let's see, vertices, draw data. Okay. And we upload the information. Okay, so this creates the data. And let's create that on the actual game creation itself. Whoops. Call renderer. Okay, we create the debug information. Then let's see if we do something like draw debug, then do we end up drawing stuff then? We do. Okay. But right now it kind of like discards all of this. And we probably want some kind of debug frame data. Debug data. So we will allocate these, and instead of let's see, we will access them by instance frame data. Debug data vertices. Also, we will clear it. We pass along the indices here. Okay. So our debug packets now contain our lookup information as well. So now we can actually also update the color itself. This should still work. And we can simply do something called draw debug. That is fine. We could also do something like static void. Update color, debug color. No, let's just do update debug data. Now let's see, a const unsigned int here. Index. a float x, const float x, const float y, const float c, and Directx float xm float 4 color. Okay. Create mesh. It's after the before that. Okay. Okay. So let's see, because this information here. Maybe we just want. We could also just pass in the current selection. Yeah, we could do that. That would make it make us able to not clutter the code. Selection. Right. Yeah. Yeah. Let's just do that instead. Renderer. Yeah. No need to handle that right there. Hello. How are you doing? Let's see, and in our renderer. Uh, let's see. Int selection index. So yeah. Okay, so we simply store whatever selection index we had. We check. And the instance frame data, debug data, selection index is unlike um, The invalid index, we know we need an update because we suddenly have an index which is not set. Therefore, we set it. Then we want to grab, what do you call it? So this is happening for, yeah. Okay. So the packets themselves mirror the actual AABBs. So if we did something like instance frame data debug packets at the selected index, we could compile a let's see. Actually, I'm unsure whether I want to store the offset as well. Oh, we always know the vertex count, right? Okay. And we don't need to modify the indices. Unsigned int offset. And we create 8 vertices. Unsigned int count equals 8 for a box. So we want to modify for offset I less than offset plus count, and we increase this. Okay, so we access our frame data here, debug data, vertices, color, and set it to red. Instead. And we call the create update function here on the back end of the renderer. Let's see if this makes us crash. Shouldn't, but nothing happens. Let's see if I can spam the console here. Ran. No, it doesn't run. $41, $43. Okay, it's of course because Yeah, now it gets marked as red, right? Yeah, but I can't click on anything else. So if it's the first time, okay. So if it's deselect all, that is the case right here. Okay. Old. Add. And we do the same thing here. Just with this and let's see. And we reset this. There we go. Should be fine, right? Oh well. I mistyped somewhere. Let's see. Yeah, this doesn't work because okay. And we pass in the game state previous selected index here. And we use that instead. This case is still fine. Let's see. Let's see. This should reset it, right? Okay. And this is different from the, yeah. Let's see, let's just test how many calls we actually get to this log here, or scope here, call. And let's do call 2. Call 1. Call 2. Okay, so it only happens once. Great stuff. I'm suspecting if I disable this part and just do something like this, I will be spamming call whenever I select, yeah. That was the reason why I saw a performance hit. Okay, so whenever we update this selection, we actually update the color, otherwise we don't. And where did I... Oh, I introduced a bug / error right there. Okay, and we're back with a different rendering algorithm. Oh, of course the movement doesn't work. Okay, okay. Yeah, maybe we just want to yeah, static void update abb debug data, and let's do a constant sign int index, not maybe just abb's and index. Maybe just the abb. And we would recalculate the vertices here. So sort of like this, but we won't be building the indices. So the color is correct. The there we go. Let me see. We built a series of vertices here. Okay, we do like this instead. Okay, let's create another temporary here. I really need a break, so I'll be doing that very soon. Unsigned in I equals 0, list I list n temp.size I++. Temp I. Actually, I don't think I need this, but I do need the offsets. Yeah, we grab the offset, the vertex count. And we iterate over, well, this is going to be the same, so at I plus offset dot is equal to temp vertex. So we recalculate the overall bounding volume after the unit has been moved. Right now it deselects, so that's no problem. So let's add the core renderer update. Game state ABBs at let's see, offset. And this should be fine, right? Oh. Ah, yeah, okay. Why is that happening, actually? Oh, maybe I need to actually... Oh, yeah, of course. Of course. I dropped this parameter, yeah. Okay. We're back at the state we were at before the small refactor here. Things seem a bit more logical now. Um, um, yeah. Okay. And now we can actually get to the whole thing that we wanted to do, which is actually remove a unit. Um, yeah. Yeah. So basically you could just pop the unit out of the buffer. You could also do some separate logic where you disable the unit and yeah. So let's try that. Okay. Unit player, let's see, for drawing. State bool active is true. Draw index needs to go. Okay, we cleaned up that. Okay. Let's just do something like attack unit, game state. Const unsigned attack index. And we ask the game state here to set the unit attack index active to false. And if we ever encounter something, and we do not get the same halving of the frame rate as before when we did the if statement here interleave with the matrix computations, not compilations, computations, but so you can see the effect of branch prediction here. Also, we skip this state for static objects, so this is way better. You could at this stage just delete the unit from the vector, but that would kind of like require a moving of several units. So yeah, we could play around with different implementations, but I think this will be fine. Okay, so let's see. Let's see. Let's get an unsigned int. Get unit index. Const unsigned int x. Const unsigned int y. Let's see. Okay, so this returns the unit index of a particular tile. Uh, unsigned int attack index. Um, let's see. Okay. Game state. Okay. Let's see. Oh, it's by the tile click. Okay. And we actually delete that. Next, we should probably disable the ABB as well. Yeah, we should handle the cleanup of that. But as you can see, I can still actually select yeah, ABB. But yeah, we could add some selection logic in terms of the unit being active. Yeah, so if and the game state units. Let's see. At least now I shouldn't. Oh, I can still select it. Let's see. Well, that shouldn't work, right? Ah, yeah, okay. So this is not possible, but let's just do it in the actual grabbing algorithm here. Okay, if it's not active, else. And let's just invalidate the index here. Yeah, okay. I need a bounce check. Yeah, now I can click on it, which is great. So the last thing we need to do is actually disable the whole what do you call it? Maybe we actually want a yeah, we could do something like active here. Full active true. If continue, and then we don't need this. And when we attack the unit, right? Mm, plus game state tile rows. So this should be the same. We simply can't yeah, we can't select it. Let's see, when we attack. Um, yeah, so we can set the ABB to disabled, and then we won't be able to click on it anymore. Yeah, let's do a bool reset equals false. And bool reset if reset not reset, we set temp equals to this, otherwise we set temp to resize 8. Yeah, and we can ask our renderer here to let's see, maybe we just want that. Let's see, unsigned in overall offset. And we game state. Okay, there we go. So we don't delete the ABB, but we simply remove it. And last, we need to there we go. Ta-da! Great stuff. And this is fairly performant, so and this is um, this should not be built into a release runtime build. We could simply add a preprocessor check here. Okay, great stuff. We modified our algorithms here to actually allow us to quote unquote delete stuff and not render it anymore. It's actually still um, inside of memory, and we don't really care about that. We can expend memory on a couple of extra units that we simply don't draw. The more performance heavy costs are actual rendering and computations of the actual transforms. And we kind of like decouple the calculation of the transforms. So now the application itself, the game itself, only cares about world space positioning, the material and the mesh, and of course some scaling stuff. And the renderer itself cares about let's see, it cares about the actual render side information in terms of the mesh information, the things that it needs to do the actual vertices and indices into our index buffer, the materials, and of course then the calculation of the transform, which is passed along. So this also allows us to do efficient frustum calling on the CPU side in case we got a lot of objects. So this is way more scalable. And these few computations here, well, in general, it all could be vectorized for even more performance or split into separate threads. But right now, it's really overkill to even consider that at our current use case. So, yeah, we refactored a bit of the renderer. It has way less methods now. And a better workflow, I think. The responsibility of the different systems have been decoupled, and we do not any longer have any parallel data structures that need synchronization between the systems, maybe except for the debugging information. But yeah, the debugging information is not something that we would want built into a final product anyway. So you could simply do some sort of, well, yeah, you could do some optimizations in terms of if you wanted to submit your debugging information dynamically as well. You could do vectorized updates of well, you wouldn't have to update anything, but you could actually just move the whole the whole computation of the actual lines to the GPU instead. You could also do batched draw calls, instance draw calls. Yeah, you could optimize it in a lot of different ways. Anyway, I'll definitely do a break for now. Maybe I probably won't get back uh, today, but yeah, we'll see. But I hope some of you guys found this entertaining or helpful. Um, Hopefully I'll be seeing you around here on this channel, and yeah, if you want to support or join the community, there are details about how to do that in the description. Of course, feel free to comment, like, or subscribe. Yeah, all right. Please take care, everyone. Bye bye.